Hello, everyone. This is the video for your second party, the midterm number 2, which is scheduled on Wednesday, April 8th during our regular class time. So this time I'm going to kind of summarize the important contents that we covered in each chapter. So, and then talk a little bit about the format and how I can manage this online testing. Actually, this is the first time for me too, so I hope it is going to be, you know, it's going to be okay and pleasant experience for everyone. But I'll try to do my best. Okay, so this is midterm number 2. Okay, let's see here. So midterm number 2, also known as our party, right? Okay, the schedule is Wednesday, April 8th. So this coming Wednesday during our class time. So it's going to be 8:15 to 9:15 a.m. This is Pacific time. And the chapters covered 4, 5, and 6. So I'm going to talk about the topics for each chapter today. And this is open book, open notes, so that you don't need to, summarize and make the formula sheet this time. And of course, AISC manual as well. So basically, I totally understand the situation, and based on the current circumstances, it's really hard to assess your performance accurately, like we did in the the classroom setting and the one-on-one. Oh, I mean the face-to-face setting. So that's what I'm making into the open book test, and we'll see how it goes. Okay, and so what I'm gonna do, I like to post the problems on the Blackboard. So it is gonna be on Blackboard. And make it available during this time, 8:15 to 9:15. And I'm gonna add 15 more minutes at the end, so that during this time, what you're gonna do is you need to take a picture of your work using your cell phone, and then convert that into the one PDF. Okay, so take pictures of your work and then convert them into one PDF. Okay, and there are a lot of applications on your cell phone, either Android format or the iOS format, that you can easily convert your pictures into one PDF files. Not only just make it into PDF version, but also there are a lot of different functions to compress the file size so that it is going to be a reasonable size, so that you can upload it on the Blackboard as well. So the timeline is you will have a 1 hour, 60 minutes to take the test. After 9:15, okay, you have 15 minutes to convert this file into the one PDF so that you can upload it into the Blackboard. So I'm gonna post the problems on the Blackboard. Let's see. You will see some problems. It could be conceptual problem. It could be the calculation type problem. But it is open book, open notes, the test. So if you're familiar with the material, it should be enough time to complete all the problems. And at this time, as I promised earlier, I'm going to have one bonus problem so that you can, show your performance in addition to the regular problems. And then I'm going to maintain my office hours. I'm currently maintaining my office hours during the weekdays and even during the weekends. If you really want to make an appointment with me, try to have a one-on-one WebEx section, WebEx session, I can do that. So if you have any questions, I'll be available through emails and WebEx. This is online virtual office hour session. I can maintain it. So just send me an email if you have any question. If I can easily get back to you via email, I'll do that. If the explanation is too much using email, then maybe I can make an appointment with you so that we can go over the problems again together through the WebEx session. All right, I think that's all for the logistics. Okay, so let's talk about each chapter. Okay, so let's start with chapter 4. So chapter 4 is a design of tension members. So in chapter 3, and from the previous the test, we talk about how we can analyze the tension members. We considered basically two limit states, yielding and rupture, and depending on the arrangement of the bolted connections, sometimes we have a block shear failure, would be additional limit state. In this case, chapter 4, we're going to focus on the yielding and rupture. So two limit states, yielding limit state and rupture limit state. The typical equation to calculate the nominal value of Pn. For yielding limit state, it is Fy times Ag. So we use a gross entire area times the yield strength of the material. While this rupture limit state around the holes, so it's going to be Fu times Ae, and this Ae is shear lag factor U times An, and An is the net area. So all these basics are covered in chapter 3. So I hope you already have a good understanding about those. Now, this is the design. So difference between analysis and design, we always satisfy this equation, design equation. Capacity should be larger than or equal to the demand. In the design problem, we always start from the demand calculation. So based on the given load, find out the target demand, and when you equate that demand into the minimum required capacity to select your section, that's how we solve the problem. So these two equations are now rearranged to find out the minimum area with a given material properties. In this case, AE is a function of AN, and AN is also a function of AG. So these equations are available in your textbook. By the way, depending on your methodology, we have two different methodologies, LRFD and ASD. And we use omega factor for ASD, phi factor for LRFD, right? So let's look at the LRFD first. The factored the capacity using LRFD method, for yielding, it is going to be phi times Pn, which is phi times Fy times Ag. So this is the yielding limit state. So when we rearrange this equation, and this is the factor capacity that should be larger than or equal to our the demand in LRFD is going to be Pu. This is a factored demand. So when we rearrange to find out this minimum required area, so that we can say minimum Ag will be equal to PU divided by everything else. So PU over phi times Fy. And this is the equation number 4.1 in your textbook in page 108. ASD, this is very similar. It is going to be Pn over omega, which is Fy times Ag over omega, and that is the capacity that should be larger than or equal to Pa in this case. So when you solve it for Ag, everything else go the other side. So Ag is going to be larger than or equal to phi times Pa over Fy, so that minimum Ag will be equal to phi times Pa over Fy, right? Okay, so this is about the yielding limit state. And then also we have to consider the rupture limit state. And by the way, this is the equation number 4-2. Actually, ASD entire thing is 4-1 and 2. The LRFD, sorry. ASDs are 4.1a and 4.2a. So anyway, these expressions are all available in your textbook. Rupture's limit state is a little bit complicated because it is not directly into AG. This is in AE, and AE is equal to U times AN, and AN is actually AG minus area of the holes, right? So because we do not know the amount of the area of the holes at the beginning, they go on to the several steps, and those, it's not a long derivation, but all the steps are available in your textbook. So finally, the minimum Ag equation for against the rupture limit state is equal to Pu, the factored demand, divided by phi times Fu, and shear lag factor U here, plus estimated area of the holes. And the area of the hole. So it's not AN, it should be AH. So this is going to be area of holes. And this is the estimation because we do not know how many holes are required and needed. Similarly, we will have the similar equation for minimum Ag against the rupture limit state using ASD. That is equal to omega times Pu. Omega times Pu over Fu times U plus estimated area of the hole. Okay, so using these two equations, we will determine the minimum required amount of the gross area of your section, and based on those two values, we will make a selection. And example 4-1 will be the good starting point. 4-1. This is in your textbook page 111. And also, by the way, I posted all the solutions for the previous entertainment package. Number 4 and 5. Number 6, actually, that's the repetition of those example problems in your textbook, and the solutions are already available, so I didn't upload any solution for homework number 6. 4 and 5, I already posted those solutions on the Blackboard, so you can look at it. So example 4-1 is going to be a good example problems to exercise this chapter 4. So that is all for chapter 4. Now I'm going to go on to chapter 5 and 6. Okay, chapter 5 and chapter 6 are actually related. So chapter 5 is the analysis of compression member, which is the column. right? And chapter 6 is the design of the column, okay? So in chapter 5, we talk about how we calculate the nominal actual capacity against the normal forces. And we also talk about the failure mechanism. The typical failure mechanism is going to be the buckling. And then using those concepts in theory, in chapter 6, we determine what is going to be the lighted section based on the given loading. So we talk about the chapter, the design of the columns. So let's begin with the chapter 5. In this chapter, there are a couple of concepts that we studied. The first one was the residual stress. So residual stress is kind of excessive of the stresses which has happened through the manufacturing process of the steel section. So when we apply very high hit into the raw material and we change the shape into, let's say, W shape or hollow section or T shapes or whatever shape, and when those hot material, over time is going to be cooled down, and we have a difference in kind of a timing to cool it down the different sections. So with that reason, we have a uneven distribution of the stresses, and that is called the residual stress. So we talked about that. We also talked about a buckling failure. So this buckling is a typical failure mechanism for the column. And to understand this failure mechanism, we started with the Euler buckling. Euler buckling, which is a very ideal situation that we have a pin boundary condition. So we were able to define how we can calculate the critical force, P sub CR, from their F sub CR or vice versa. So P sub CR is going to be the critical force, F sub CR is a critical stress against the buckling failure based on the pin boundary condition. So P sub CR was, using the Euler buckling failure mechanism, pi square EI over L square. Okay, so our calculations and all the formulas based on the AISC manual was based on these. We also talk about the effective length. So effective length is a KL. So K is the effective length factor. So this Euler buckling is based on the pin boundary conditions, but in reality, we may have a different boundary conditions like a fixed or combination of fixed and pin. If we have a side sways allowed, then this K factor, the minimum value is 1 and larger than that. So effective length is the length used in our calculation, and using that effective length, KL over R is called the slenderness ratio. And this is very important indication. So KL over R is everything actually in the column analysis and design. So you might remember this. This is P, N. And by the way, this is the same. The chart is available in your textbook. This is in terms of F sub CR. So, okay. So to be identical and same as your textbook, this is going to be F sub CR. So initially we have the yielding limit state is the governing the critical force, because when the slenderness ratio is small enough. So it is going to be kind of constant. And after that, it is a linear function and then linear. So this is the short column, which that the buckling is not going to be the governing failing mechanism. Now this is the inelastic buckling range, and here is the elastic buckling range. So this is available in your textbook. Here we go. Figure 5.7. Okay. Figure 5.7. And the borderline between the inelastic buckling and elastic buckling is here 4.71 square root of E over Fy. So if your the slenderness ratio KL over R, or in your textbook they use the L sub C over R, L sub C is the effective length KL. The same thing, okay? So if slenderness ratio is less than or equal to 4.71 times square root of E over Fy, then we're going to be in the inelastic buckling range, and we just compare to the yielding limit state, so that the smaller is going to be your capacity. If your slenderness ratio is larger than this, then inelastic buckling range, and we have a different formula. So the formula for F sub CR is going to be, for inelastic buckling range, F sub CR is 0.658 to the power of Fy over Fe, Fy over Fe times Fy again, while this elastic buckling range F sub CR value is going to be 0.877 Fe. So I explained this a couple times in the class that inelastic buckling range is not good because, as you can see, this F sub CR value is just a function of Fe. Fe is, by the way, pi squared times E over KL over R squared. So I'm going to write down the Fe equation here. Pi squared times E KL over R squared. So as you can see, this Fe is not a function of the strength of the material. This is just a function of the Young's modulus, which is the stiffness. So when you decide to use a high strength material, but your column is within this elastic buckling range, which is not good because you don't have any benefit by using more money to have a higher strength material, because it doesn't really affect it by the high strength material quantity. So anyway, the slenderness ratio is really important. That will determine which case, which equation that you're going to use. So that's the analysis. And one more, there are, let's see. So the way to calculate the capacity, and these three methods are going to be used in the design as well. So the way is using the equation, and these are two equations that we have, right? Depending on the elastic and inelastic buckling range. The second one, so for calculating phi times F sub CR, or P sub CR in this case. So phi times PCR or PCR over omega, depending on, this is a LRFD ASD, right? So the first method is equations. Second method is table 4-1 for W shape, and there are several other tables for hollow sections and so on. And the third method is going to be table 4-14. So we went through the example problems. By the way, the examples 5-2 and 5-5 and other entertainment package problems, I think EP number 4 and 5 are good exercise for covering this chapter. Chapter 5. Chapter 6, examples 6-1 and 2, which is the the entertainment package number 6, would be a good exercise to cover chapter 6, the design of the compression members. So basically, we're going to use these three methods. Equations, depending on slenderness ratio is less than or larger than this, we're going to have two different methods, the equations to find out f of CR, and multiply by AG is going to be piece of CR. All right, table 4-1 and 4-14, the difference between these two is this. So table 4-1 directly gives you this table 4-1 directly gives you phi times p sub CR, or PCR over omega value based on the effective length. So we have to have the KL, and then we will have factored capacity directly. While this table 4-14, we are using slenderness ratio instead of effective length, so that we'll get phi of f of CR, or f of CR over omega value. So we covered example problems like this. If we know that the weak axis of the column will be the governing axis, okay, based on the boundary conditions, we do know that, and we have effective length is given, then you can always go to table 4-1, because table 4-1 is constructed based on the KL value with respect to the weak axis, y axis. But some reason, based on the different boundary conditions, or sometimes we already knew that the y-axis is always a weaker axis, so we have additional bracing into the y-axis to make the strong axis is going to be the governing axis. Then we cannot directly use this table 4-1. Of course, there is a way to use this table with a small calculation later on. But in that case, table 4-14 would be better, because we can easily calculate the slenderness ratio. So determine which axis is going to be the governing axis, what is going to be the governing slenderness ratio. Go to this table, find out either f of CR with phi factor or omega factor, depending on the methodology, and then just multiply by AG based on the selection. So these are three different methods, and these example problems are going to be the good exercise problems for preparing the exam. So I think this is kind of a short summary. I didn't go through all the details in this video, but hopefully you can find out the background of this materials. We already went through the classes, and all the PowerPoint slides are available in your Blackboard, and I uploaded the solution for the entertainment package problems. So this would be a good kind of overall summary to prepare your midterm number 2. So again, the exam is going to be on Wednesday from 8:15 to 9:15, 1 hour. That's going to be available on the Blackboard, and I'm going to add 15 minutes at the end. So actually that exam is going to be available from 8:15 to 9:30, but that 15-minute is the time for you to prepare, just convert your pictures. So you have to take pictures first of your work, and then convert those pictures into the PDF, combine everything into one PDF file, and then upload it on the Blackboard. So that 15-minute is there. So I hope you can finish all these problems until 9:15, and then you have full 15-minute to convert those files into the PDF format and upload it on the Blackboard. Okay, and if you have any questions until Wednesday, just let me know. During your exam time, I'll be available to check my emails or whatever. So just contact me at any time if you have any technical problems, or challenges, or if you have any questions based on the problems or whatever, just shoot me an email. I'll do my best and respond back to you as soon as possible. All right, thank you, and see you later.